So I'm going to introduce here our fellow Ingvar Kirchner. Ingvar has more than 37 years industry experience in open pit and underground mining, drilling, mineral resource estimation, and associated geostatistics, reconciliation studies, technical audits, and due diligence studies of a range of globally diverse projects. He's a fellow of the Australasian Institute of Mining and Metallurgy, member of the Australian Institute of Geoscientists. Ingvar is a competent, qualified person for mineral resource estimation, public reporting for a wide range of metals in accordance with the key international reporting codes. So, welcome, Mr. Ingvar, please.
Thank you to Datamine for giving me a moment to come up and talk to you a little bit about MIK stuff. Somebody pointed out the other day that MIK is one of those things that's hardly new. It's been around for 40-some years, and yet it still serves a purpose. So let's go. So I was really just going to talk about, why we might use it, and a little bit of how it gets implemented. I guess when you're sort of winding up to do a resource estimate, there's a bunch of stuff that you do need to consider. And one of the things I'd like to hammer is that I guess a resource model and the methods that you use do need to be appropriate to the style of mineralization and the need that model's going to address. So you do need a range of tools at your disposal. You can't just keep hitting it with the same hammer all the time. Truly, like if you're looking at thin veins, should ponder using something like accumulation. And when you've got some deposit that looks like a dog's breakfast, MIK can probably help you out. And when I'm sort of giving you that hideous image, what we're doing is trying to assess the continuity and consistency of that mineralization, both at a structural or geological level and the grade, and the continuity also at the scale of the available drilling. I mean, sometimes you get those deposits where you just know that you're never going to have enough drilling to absolutely pin it down. So you do need to have options. You also get that situation where very early on in a project development phase, you need to have a model that works correctly across a range of cutoff grades. Within limits, it's got to be able to. Well, you don't necessarily know what the cutoff grade is going to be when you develop some models. And you also know that they're probably going to want to play high-grade, low-grade stockpiling games when they're trying to pay off things at an early stage in a deposit. So you need to have something that's flexible. And sometimes ordinary kriging just on its own doesn't quite do that. That style of mineralization kind of makes it risky business if you're dealing with stuff like stockworks, sheet of veins, alteration, disseminated type mineralization, or some hideous combination of all of the above. Quite often these things will have variable orientations, and you can't address all of them and at the same time. Sometimes there's clustering of the mineralization. Sometimes there's clustering of the data in the clustered mineralization, and quite often a lot of structural type things that we're dealing with are short. Like they literally do not extend from one fence of drilling to the next. And the grade variability can be really extreme in a lot of systems. And if you haven't seen one of these, you will eventually. It's coming. So this is kind of our problem in a nutshell. Take this as a fractal type situation, a very compressed example of a much larger problem. There is no right way to drill that one that is going to give you the answer. And if you blew this up to be a deposit scale type feature, it happens. What you can see in there, there's a couple of primary orientations, but there is an edge to this whole system as well. So I know it's a little bit hard to see in the image, but you know, handed a bunch of drill holes through one of these typical systems, you know, quite often you can look at it and pick up, you know, a primary orientation and some secondary orientations, and I guess you know, some of the key takeaways would be that you can look at this stuff, an individual high grade in some drill hole, and find another drill hole that really is honestly not very far away from it that will just be entirely different, and that's your lot in life to deal with. It's real. You know, sometimes these things, they're not necessarily through-going veins. It might be alteration systems, might be disseminated stuff. Anyhow, you've got to deal with it. The other thing that you're going to say is that the interpretations can't really be robust without good geology. I can pretty confidently say that if I put this out to the room, you know, out of 6 geos, I'd probably get 12 different interpretations of what that might look like if they tried to throw vein interpretations at that. Now, this isn't by any means the worst of a selective interpretation that I've seen. You know, quite often people turn these things into spaghetti monsters, but in this case, all you can say is that, you know, yes, the grade is highly variable between adjacent drill holes. Structurally, there's little certain continuity. The orientation that they opt to drill in on is pretty simplistic. And you look at that and say, well, I could come up with an alternative interpretation, and that's a challenge. And there's mineralization that gets ignored in the whole thing, especially if they try to throw thin veins at it. Yeah, so there's also mineralization that gets ignored. And also applying some of these sort of discrete interpretations on things, that sort of interpretation is only appropriate for the cutoff grade that was used for the interpretation. You know, give or take a little bit. It's not going to function across a range, and does nothing for telling you how it's going to be mined. What you can do is sort of stand way back. There's always a geologically controlled second order envelope to the system, and you can say with a high degree of confidence that is the envelope. You know, this isn't the most beautiful example. You might not catch absolutely all of the mineralization, but there will be a corridor to the thing that you can trap. And the nice thing about MIK is that envelope doesn't need to be precise. If you have a little bit of waste in the system on the margins, great. It kind of wants that. Stationarity, I raise that there because in these sort of systems, you can imagine inside of that envelope with all of the rubbish that lives in there, you don't have stationarity, and the process doesn't really quite need it. And I also raise the specter of the selective mining unit. It's probably one of the things that as you're wading into this, you want to give it some thought. What is honestly a selective mining unit? Talk to your engineers, and you know, probably double the size of that. So obviously, I'm winding up to take you into the MIK route on things. My approach, look, I would do this probably my own special way, and everybody else will do it slightly differently. That's okay. Obviously, there's always different ways to skin things, but I don't know. I guess I've been doing it for about 20 years, and I kind of like where I've ended up in the whole process. Generally, I just use enough indicators to discretize my distribution and things. I'm not going to show you a pretty graph. I just would hammer the point that maybe the black box approach to chopping things up in deciles and percentiles isn't always the best, because you'll spend a lot of indicators modeling the waste portion of that, what's in that distribution. So I'll put a few indicators down in the waste area, and then spend a lot of my indicators defining that sort of key cutoff grade range that defines the mineralization in the mine, and then a handful of indicators trapping the high grade tail, and then the last bin, I would jack it right up there to the point where I am not, I don't have actually all that many composites within that upper bin. And that's kind of a key decision, because, while we say MIK doesn't use top cuts directly, one of the decisions that you do make is about the bin grade for that upper bin. And I guess if you have it swinging on a handful or two of composite values, you could call it Fred, and it just wouldn't matter. I suppose as a geologist, the thing that makes me happy with the indicator process is that it treats the low grades differently than high grades, and vice versa. I guess, that's a feature that turns up in the variograms that you use for the indicator modeling. You know that intuitively as a geologist, low grade has low nugget variance and long ranges, and high grades have short ranges and high nugget variance. And usually as you sort of go through and model your variograms, you'll see that nesting feature quite strongly. By the time you get to your upper bins, it's probably nearly pure sill on the variograms, and that's okay. In terms of the estimation process, by the time you're sort of winding up to do this, we have however many indicators you want to choose. Let's say I'm using 12 that get estimated into some probability about. So you do have to watch this occasionally. I think most people do sort of set indicators below cutoff, below the threshold being 0, and above the threshold being 1. I have seen software in the past where, for some reason, a software company has done it in their black box and flipped it around the other way. That made things exciting. But anyhow, you have binary indicators, 0, 1, and you estimate into something that becomes a probability above or a proportion above, whichever way you want to look at it. And it's kind of nice that you can flip those either way. So the probabilities are somewhere between 0 and 1. At the same time I'm cranking that, I'll estimate a panel grade just for the hell of it, just to know that things are working, and I will probably also do a ranking estimate straight into my SMU blocks. So ranking estimate, I have a deliberately small search neighborhood, and it doesn't have to be really finessed to function as a ranking model, but at some point the choice of 6, 7, 8, 9, 10 composites makes quite a big difference in those estimates. So it's nice. After a while, you can pretty much just land on it. One of the things that, if you're doing the indicator modeling, I guess you need to be aware that you do need to add an order relation correction to the whole thing. And this is a worked example. I know that you can't see that, but I guess all of your probabilities need to nest. From a high probability for the low indicators to a low probability for the high indicators. And if for some reason something steps out of line there in that scheme, you need to adjust it, and it's pretty simple. The reason it would happen is that you're just using slightly different variogram models for things, and it just sees the data a little bit differently. Nothing sinister in the process. It just needs a little bit of an adjustment. So you need to do that. Now, MIK, when you first chug out those indicators into the probability fields, you must realize that the MIK product in the first instance is at point support. It's just describing the data that is found within this little neighborhood of the panel, and it's mapping out that distribution for you. So we do the CDF type validation curve, and what you've got there is the raw declustered, the raw data points there, and then the MIK model reported for well-informed blocks laid over the declustered data, and you can see that sort of matches nicely. May it always look so good, but usually if you have problems at this point, it might be that the declustering wasn't all it should be. So important point, the MIK initially is describing that distribution at point support, and you need a change of support to shift things to the SMU. I suppose it's important to point out that well-informed panel concept is kind of subjective as well, but you really just want to make sure that the blocks that you're reporting are wrapped around all of your key data, and dumping some of the extrapolated blocks that kind of just skew the whole picture for you. So if you ever see an MIK model that has not applied a change of support, if it's used for anything other than the E-type mean, I'll make the big statement that it's probably fatally flawed. And you do get that sometimes. Get the people that will just not that familiar with it, and they will assume that they've done an MIK and it's not quite finished yet. We actually need to come up with a variance adjustment factor to help us with that change of support. Now, we call that the F value, and look, it's again, sometimes it's you'd think that's fairly easy to do. You're basically taking moving things from point support to SMU support, and you have that Krig's volume variance type relation. That should work. It puts you in let me just say, it puts you in a ballpark, and it's not the end of the story yet either. I guess if you ran things at f equals 1, and I do, it means that you have no change of support, and it should sort of replicate that your declustered points for you. If you could actually run an f equals 0, basically you're moving things all the way to the panel support. So that just gives you some idea of what the spectrum of values is. Obviously our SMU is probably closer to the panel than the point, so we expect our f values to be kind of low. How low is kind of a function also of how many SMUs you're jamming into your panel. So typically, I would do all of my change of support stuff in Datamine. Again, kind of been doing it for so long that I've developed my own tools, and still doing that. I would dive out to ISATISO to run some discrete Gaussian global models for change of support models, just to give me some idea of where I need to be. In terms of the change of support mechanisms that we're using, I would personally, and not everybody does it this way, but that's cool. I would normally run an indirect log normal change of support first. I'd pick the F value that I want to target, and generate generate a bunch of F values around that target position and feed it through my macro routine. It runs an indirect log normal change of support, nudges the mean back into line, and then comes back for another smash at things with an affine correction. And the reason we do that is that, like, the indirect log normal gets you 95% the way there, but it leaves the variance a little bit out of kilter, and the affine correction just nicely touches that up for you. So don't expect you to dive into all of this, but the math is pretty simple. That's a version of the formulas almost exactly as I would use them in my routine. So that's why you get that flavor. You can go to any of the other sort of textbooks and stuff around and find variations on the formulas, and you know, it's just move things around, work it out for yourself. So it's not that hard once you get into the swing of it. References, it's there for later. So what are we doing with the change of support? Really, we're smashing. We start off with a nice a nice log normal type distribution, and a lot of times it's really a lot more extreme than that. And we're putting the squeeze on it around the mean, and there is a sort of concept of conservation of the mean. Thanks to Clayton for the graph. That's quite a nice picture of the difference between stuff at point support, what you might get in a panel, and the fact that our SMU, which represents what we expect to achieve out of mining, where we have more data perhaps, is somewhere in between those 2 points. I guess the reason I make the point there that the change of support method and the order of correction, the order of the corrections is kind of important. We use the indirect log normal because we're doing this initial smash on the log normal, or almost log normal distributed data. And as you sort of work your way in, things become increasingly normal, and you know, like the central limit theorem has something to think about. So if you paused to look at the MIK model for a selected cutoff, basically just the proportional tonnage fields of a selected cutoff sort of maps out the where most of the metal sits. You can see there it's starting to sort of highlight where the metal sits, where the high grades are, and it's certainly mapping out low grade areas. This is the old school MIK models, which have a bunch of proportional tonnage and proportional grade fields in it. I guess we're at this stage we're still looking at panels. It's not a localized estimate at all. Localization, you can thank Merit Absalov for this graph, the one good thing in his paper, that basically we're quite used to thinking of our tonnage and metal distributions as a function of cutoff grades. Well, the interesting thing is you can flip that the other way and think of it as you can discretize the same curve using fixed tonnage increments, and that's what we're doing in the localization step. It's actually quite a neat way to think of it. A bit of imagination there. So in the localization step, the LMIK approximates the likely metal distribution within the larger panels, and really, you don't have close-spaced data or enough close-spaced data, so you do take the localization thing with a grain of salt. It's just thanks to the ranking estimate, you're able to park the metal where it most likely deserves to be between those drilling fences, and gives you a shot at producing a reasonable model. Interestingly, I suppose your choice of where you park those SMUs or array the SMUs, whether they're fully 3D or a flat panel, does kind of influence the results that you get as well. But it does map out the general grade trends fairly well in 3 dimensions. I guess you've got to realize too that anything that you see here today on the screen is just looking at a very narrow slice of things. I suppose, yeah, again, look at the SMUs, and all of a sudden now we're dealing with things that are quite small relative to those drilling fences. So in terms of the final result, by the time you sort of get to the back end of things, I guess I'd just like to say that you've actually looked at this thing a few different ways. In amongst this, you've got you've got your declustered points, you've got the model report run at f=1, just to prove that your whole change of support thing doesn't have a typo in it somewhere. Doesn't happen very often, but it can happen. You've got a panel estimate down bracketing the other end of things, and we know that our SMU's got to be in there somewhere. And then in the middle of all this, we've got a variety of things. We've got a discrete Gaussian target that we wanted to hit. We've got the SMU model, the MIK SMU model, the interim thing that we can report. We've got the ranking estimate, and last but not least, we've got the final LMIK product, and they're all laying up on the same thing, which is brilliant. Again, may it always look so good. I'd point out that sometimes when it comes down to making the decision about the final F values, I would shop for an F value that would give me something that was approximately giving me the result, but it can become a bit of a compromise between looking at metal, tons, and grade. The curves look a little bit different. There's tonnage or volume, and that's on a log scale just to blow apart that high-grade tail. And that's the grade. And you can see in this particular model the grade kind of feathers out towards the very high grades. It's not a particularly high-grade deposit. It's generally meant to function somewhere down below 1.2, and it does that. So I guess what's it used for? Well, MIK, LMIK gives you a resource estimate that's almost a reserve model, and it's, I guess I'd say that with caveats. It deals with the internal dilution that you've got, but it doesn't deal with the random mining stuff that happens, edge dilution, ore loss, drill and blast. Can't predict how bad that's going to be. This will report differently to typical ordinary kriging models, and it functions across a range of cutoffs. Mining engineers will typically make fewer alterations to these things, so that's kind of nice as well. But back to the reporting aspect, you do have to word up the clients or your bosses that this is going to give you a kind of a diluted look at things. So anyhow, I think it tends to produce quite a nice result. It's pretty robust, and I guess if it gives you that opportunity to have slightly fewer tons at slightly higher grade above a cutoff grade, that's generally positive, and it really comes into play where you're dealing with some marginal project somewhere. And I guess again, MIK handles the low grades differently to high grades with multiple variogram models, and as a geologist, I really like that. Functions over a range of cutoff grades. The confidence in that result will just be higher due to the simple mineralization envelope that you drop over the whole system. Again, if you have that spaghetti monster interpretation over things, you just got to look at that and say, yeah, I'm not happy, and it's got to be reflected in the resource classification. LMIK, if you go the localization route, it's easy to use. You just have a block and a grade in it, and I guess in that sense you can also handle the multi-element stuff quite easily. You know, if you needed to, you can do that restricted ordinary creating of subordinate elements straight into the SMUs while you're doing the ranking estimates, and that's done. And I guess that's it.
Thanks, Ingvar. That was good. I haven't seen description of MIK for some time, so I'm glad to see someone still using it, mate.
Oh, look. Yes,
Yeah.
yes, I still use it.
Yeah, good for you. I did like your last comment, you know, this is what you use when the project's marginal to get it over the line, so that's always good to see. You were using Australis for the MIK, not the Datamine import of the Australis code. Have you tried the Datamine? Has it got IK? No, it doesn't have IK. It has
Look,
a Gaussian model. Have you tried that out?
no,
And compared it yet?
no, I haven't. No,
Okay,
sorry.
I'm looking for someone who has, because I tried it out and I got some weird results. So.
Yeah, no.
Anybody in the room?
The old ISATIS discrete Gaussian stuff works a treat, and
So what's your thoughts on comparing the two? What do you see that's different, I guess, is the key question there.
Sorry, which ones?
IK versus a discrete Gaussian. You've done that on the same model?
Yeah, oh yeah,
And
absolutely.
what are the differences you're seeing between those two that you think are relevant or irrelevant?
Well, look, I use the discrete Gaussian stuff to help me pick my F values, and or give me the target to shoot for. That's generally the thing that will get me there. The ranking estimate sort of also puts me in a ballpark, but I tend not to dwell on that too much. Whereas if I was doing an honest restricted ordinary kriging thing, I might. I think the interesting thing is if you calculate an F value just on the whole volume variance thing, it always comes in a bit higher than you expect, and I would suggest that, I guess as a function of your data clustering and stuff like that, the F values are lower generally, and they're predictable, but they're not. You know, like if I'm using eight SMUs in a panel or something like that, I know that my F value is going to be 0.1 or thereabouts, give or take a bit. And you know, probably if I'm running 16 SMUs in a panel, I know it's going to be a F value of 0.2, give or take a bit. It's that give or take a bit that is a challenge, and I think it just comes back to data clustering, the data that you've got to work with, and how well you model it, and your variograms are dealing with the array of orientations and stuff that you're being hit with. Like I can't probably answer that much better than that. So.
Okay, thanks.
Thank you.